Okay, thank you. Thank you very much, Oz and John. Today, first of all, previous week we have seen the Euclidean algorithm, and we are trying to find the remainder, and also we try to find the GCD, which is the greatest common divisor. Today, we are going to start with the Chinese remainder theorem. That is the first Chinese mathematician, which is a Sun Tzu, asked a question: if there's a simultaneous x, if I just what is the simultaneous number, which is the integer, which is the x, if I divide by 3 and the remainder will be 2, if I divide by the 5 and the remainder will be 3, and the remainder, and if I divide by the 7 and the remainder will be 2, what is the same, what is the one or simultaneous x is? This is the question of the mathematician asked. So in the Chinese remainder theorem, we have some positive integers which has to be prime positive integers, the pairwise relatively, and they have to be greater than 1, and the other ones of course in this case here in our modular arithmetics, as you remember from our previous course, if this is the modes and all the m's are prime numbers, and of course these a1, a2, for example in this one, m1, as far as we know, the a should be between the 0, it can be equals to 0, or it can be smaller than the modulo itself. So this is a unique solution of the modulo m. We are going to find what is the question which was asked by the mathematician Sun Tzu. So we are going to find an inverse of modulo, and it will be the multiplication of this all modulo, and we are going to find what is the inverse of this modulo. I'm going to show you one of my students cannot hear me, but the others, I think they can hear me too, I think. And also now I just opened my camera, by the way. Hello everyone. And also I use the headphone, so you may hear me very clearly, I guess. It should be better than the last week, actually. If you have a voice problem, please check your devices in your computer. Okay, for the Chinese remainder theorem, which is tries to find simultaneous x and the modulo, but please just aware that these modulos are all prime numbers. These are all prime numbers, okay? So we are going to I'm going to show you two ways or two alternative solution way. Okay. I'm going to show you two alternatives, okay? At first, we may use a table. Okay, in this table, I'm going to create a table. Okay, first of all, we are going to write the remainders. We have three modular equations. The remainders are given here, which is 2, which is 3, and which is 2. Here is the modulo 3. It is the modulo 5. Yes, it is a modulo 7. Okay, in that case, at first, our first column of our table is remainders. The other one is the modulo but specified. What is the modulo specified? So we are going to calculate for the first step, calculate the grade modulo. What is the grade modulo? You can say that is mg, for example, which is the modes, the multiplication of the modes, which is m1 multiply m2 and multiply m3. The modular grade, the grade modular is, in this case, 3 multiply 5 and multiply and 7, which is 105. And the modulo specified, for example, modulo for this one, let me show you here. The modulo grades divided by the modulo 1, which is 105 divided by, for the first one, which is modulo 3, is 3, which equals 35. Okay, so we can say that the modulo, this one or 1, equals 3. Sorry, 35. Okay, for the modulo 3, the modulo specified for the 3 or modulo 3 equals 35. So the other ones is the same. For example, this one is 21. Why? Because it is, let me show you here, which is 105 divided by 5. Or it is actually, as we know that the greatest modulo is multiplication of these 3 of them. So for example, for the 7 here, for 3, we can say that it is multiplication of the rest of it. For example, 3 and multiply by 5, it is 15. Okay, and the other one, the next column is the inverse. Inverses. What inverses is actually? I'm going to write the same color, let me say. So here, it means that we are trying to find the inverse of the modulo of this one. This is our modulo specified, and modulo specified multiplied by x. We don't know what the x, because it is the inverse of the 35, should be congruences as 1 in modulo 3. And this is the same for the rest of it. 21, I have to find, and this is the x1 and this is x2, and that x2, if I multiply by 21, it has to be, the remainder should be 1 in modulo 5. Okay, and this one too also, this is the same. If I multiply something else, what is the integer? We don't know what till now, and it has to be 1 in modulo 7. So in this case, what is the x1 and what is the x2 and what is the x3? So let me do this one here. For example, 35 multiplied by x should be 1 in modulo 3. So in this case, we can rewrite, or we can write that the 35, if I divide 35 by 3, what is the remainder? Is there anyone else? I guess no. Yes, Abdullah Azam. Do you think? Yeah, Shalit, yes. It is 2. If I divide 35, the remainder will be 2, right? So I can rewrite as 2 multiplied by x. Maybe the remainder will be 1 if I divide by 3. What should be this x? So as far as we know, x should be between 0 and is smaller than the 3. So if x is 0, then the remainder will be 0. If x is 1, the remainder will be 2. If x is 2, the remainder will be 1, right? So we can say that x is 2. Did you understand? It means that which x I have to multiply by 2, and if I divide the result by 3, the remainder will be 1. So x can be 0, 1, and 2. This is the choice set of this x. So if I multiply by x by 2, if x is 0, the remainder will be 0. If the x is 1, 1 multiplied by 2, the remainder will be 2. If the x is 2, 2 multiplied by 2, it will be 4. If I divide 4 by 3, the remainder will be 1. So the result, or the x, we found that is 2. So here we can say that x is 2. So it is the same for the rest of it. For example, 21 multiplied by x2 equals 1 in modulo 5. So 21, we can say that if I divide 21 by 5, the result or the remainder will be 1. So I can rewrite as 1 multiplied by x2 equals 1 the modulo 5. What might be the x? And x should be one of this number. So it is very obvious that x2 should be 1. Because if I multiply by 1 by 0, if the x is 0, the remainder will be 0. If I take that x is 2, 2 multiplied by 1, the remainder will be 2. If x is 3, if I multiply by 1, the remainder will be 3. If x equals to 4, if I multiply by 4 by 1, the remainder will be 4. In this case, the x2 equals 1. And it is the same for x3 too, because if I divide by 15 is divided by the 7, the remainder will be 1. So the inverse of this number is 1. Did you all understand? Is there a question with this one? So let's continue then. This is our inverses. So we found the inverses. Now we are going to create the results. To multiply these all. Which one is 2 multiply 35 multiply 2 equals, also this one at first 3 21 multiply by 1, and this one 2 multiply by 15 and multiply by 1. Okay, this one, what is the result of this one? It is 4 multiplied by 35, it will be 140. And this one is 3 can 6 work? What it means? Work. So for this one, I guess you are asking for the modulo 5 for x2. Yes, It cannot be because it has to be smaller than the 5. In modulo, please remember that, for example, x or multiplied by y, for example, equals something else. Let's say it is z, but in modulo 5, which means that everything x, y, and z, they has to be smaller than the 5, and they can be equals to 0. Okay, that's why we do not take 6. But it doesn't matter actually. In the end, you can take it. Okay, so here we continue with the second one, which is 3 multiplied by 21 multiplied by 1, which is 63. Let me change the color, by the way. Okay, it is 63, and this one, it is obvious that it is 30. So we are going to take the summation of these 3 results. Okay, this is you can say that this is result 1, this is result 2, and this is result 3. And I'm going to continue from here, which is the results of I, which is 140 plus 63 and plus 30. What it is 233. Okay, so now we found 233 here as a summation of all the results. Now we are going to find, I'm going to use that space, unfortunately. And what is the image of this 233 in modulo 101? Okay, if you do the mathematics, what is the result? Let me do it here too. Use my calculator. 233 in modulo 105. And I found that it is 23. This is our result. It means that the simultaneous x, one of the simultaneous x might be 23. This is our result. Is there any question for this approach, for this way? This is the first alternative of the solution. The first alternative. Is it okay now? Okay, that's great. Now let's continue with the second alternative. Let me write here. So in the second way, we are going to start with the last part, last step, which is here. So in this case, if I can write, let me do it here. Let me do it here. This is step 1. If I divide x by 7, if I say that this is k, and the remainder is 2, right? So I can say that x equals 7k plus 2, right? That's great. So for the step 2, we have finished that part. Now we are going to continue with the second step. So, but here our x is equals 7k plus 2. Now we are going to write here 7k plus 2 equals 3 in modulo 5. So I sent to, or we can use as, for example, this is the 7, which is greater than the 5, but we can use it as 2k plus 2 equals 3 in modulo 5. At first, you have to decrease, or you just make the modular arithmetics and just try to find the integers which are smaller than the modulo itself, which is 5 here. So I just changed the 7 as 2 because they are the same in modulo 5. Okay, so here we can say that this is 2k, and I sent it to the other side, which equals 1 in modulo 5. So what might be the k? The k maybe, or the choice set of the k equals what? 0, 1, 2, 3, and 4. 3 and 4. So if k is 0, then the result will be 0. If I take the k as 1, and the result will be 1. If I take the 2, the result will be 4. The remainder will be 4. If I take the k3, if I multiply 3, the result will be 6. And if I divide 6 by the 5, the result will be 1. So we can say that k equals 3. Right? So now we are going to show the k as we have did for the x in the previous step. So we can say the k, if I divide by 5, there's I, let me say, and the remainder will be 3. So k equals 5i plus 3. Okay? So in this case, we are going to show you, this is the first one, let me write here 7k plus 2. That will be our x, and it has to be equal to 3 in modulo 5. And here we are going to use that k as this expression. So here I'm going to continue with the same color. 7 multiplied by 5i plus 3 and plus 2. It has to be as x is our x, which is 35i, and plus 21 and plus 2, which is 35i, and plus 23. Now this is our new x. Now we are going to start with the third step, step 3, which is here. So we have an x equals 35i plus 23. It has to be equal to in modulo 3. At first, what we are going to do in the explanation or in the expression, which numbers are greater than the modulo itself, which is 3 in this question, we are trying to write in modulo 3. For example, what is the remainder of this 35, which is 2i, plus what is the remainder of the 23 is 2, equals 2 in modulo 3. So we can say that 2i equals 0 in modulo 3. And we know that the I, the choice interval I, could be 0, 1, and 2. That's all. So what might be the I is here? Yes, of course. No one is here, I guess. So I should be 0. So we can say that I equals, or we just can rewrite as, if I divide I by 3, this is uh, y, let me say, and the remainder will be 0. So 3y plus 0 will be equal to I. So here I am going to rewrite in the previous step. Here the x equals 35 I plus 23, and now inside of the I, or instead of the I, we are going to rewrite that expression. We are going to use, and now we can say that x equals 35 multiplied by 3y plus 0 and plus 23. So here x equals 105y and plus 0 here and plus 23. As you see here in the end, what we found that x equals 105y plus 23. This is our greatest modulo, and here is our simultaneous x. If you want to check the result, for example, if you divide 23 by 3, the remainder will be 2. If I divide 23 by the 5, the remainder will be 3. And if I divide 23 by the 7, and the remainder will be 2. So this is the result of our second alternative way. So no one in the course now, that's why I'm going to skip the next question. So use the construction in the proof of the Chinese remainder theorem to find all solutions to the system of congruences. Use two methods. At first, let me check if I just give a space for myself. Okay, that's great. So this is the question. So I'm going to give you 5 minutes to apply this at first the table method, and then also I'm going to ask you for the second method. If anyone can solve that question, I am going to award that person. Did you understand, my friends? Or is there anyone else who listened to the course? And that's great. That's great, Yasin. You are very close to 5 points. What you have to do at first for the tables, you are going to construct a table. For the first part, At first, you should create a table and you have to write the remainders which are given in the question. And then you have to calculate the greatest modulo, which is the multiplication of all the modes which are given in the question. We are going to multiply this all, but we are going to use that greatest modulo as a mode. But not now, but in our table, we are going to mode specific for the modulo itself. For example, this is our modulo 3, and we use that one, for example, 105, which is our greatest modulo, and we divide by 3, and the remainder, the result will be 35. So this is its modulo, which is 35. And the same procedure we have to follow for the modulo 5 and modulo 7 too. So here, for example, in modulo 5, the greatest modulo is 105. And if I divide 105 by the 5, which is our modulo itself, so the result will be 21. For the mod 7, if I divide by 105 by 7, the result will be 15. So it is very easy to find the modulo specified for the mod itself. And then we are going to find the inverses of these specific or specified modulos, which is 35. There should be an x, which is x1 in this question. And if I multiply these two integers, the result or the remainder will be 1 in modulo 3. It means that there should be an x, which is x1. And that x1, if I multiply x1 by the 35, and then if I divide by the 3, the remainder should be 1. This is what the inverse is, actually, as you remember from our previous week. So the x equals 2. This is the explanation, how we found the x. Here, this is the explanation. So this is the same for the rest of it. For the mod 5 and mod 7 we are going to do. And then as a result, we are going to multiply the inverse, the remainder, and the modulo specified. And as a result, we have 3 lines and 3 results. We are going to take their summation of all 3 results. And this summation, we are going to check what is the remainder of this summation if I divide by the modulo of the grade. That's the way, for the first alternative way to solve that question. So this is our question. Okay, Sarah, we are going to solve together, and then we are going to check your results. But how could you find modulo 313? Because if I multiply 3, 5, 7, and 11, it has to be 1155, which is our greatest modulo. You may check your results, Sarah, but thank you for your effort to solve this question. Okay, let's start together. Is there anyone who needs extra minutes? But that's enough, I guess. We are going to apply for first alternative. This is the first way. The first way is it doesn't matter. It has no name as first alternative or second alternative. Okay. Yes, Azam. Yes, you are right. So first one, the first alternative, which is the table. I'm going to create table. So what is my table? The remainders and the specified modulus and their inverses and results we are going to have. Okay, what are the here also we should write, sorry, by the way, just clean this part. At first I want to say that it's modes and then remainders and the modulo specified and their inverses. And then we are going to take the results. But after the inverses, I'll just try to arrange my space. So what is the modes? Mode 3 we have, and mode 5 and mode 7. Also we have mode 11. As you realize that these all modes are prime numbers, okay? So what are the remainders? Remainders are also given in the question, which is 2, 2, 3, and 1. 2, 2, 3, and 1. So what is the modulo specified? What is the modulo? The greatest modulo. The greatest modulo equals 3 multiplied 5 multiplied 7 and multiplied by 11, which is 1155. So this is our greatest modulo. So we are going to find 1155 divided by the modulo itself, which is 3, equals 385, I guess. Please check, my friends, by the way. And if I divide by 1155 divided by 5, which has to be 231. 31, this is 1. So if I 1155 divided by the 7, which is 165, I guess, and 1155 divided by the 11, which is 105. Could you please check the results? This one, this 385, 231, 165, and 105. I guess they are correct. So thank you also. Thank you very much. Now we are going to find the inverses. Inverse of 300, 385, 385. There should be something else. I have to multiply by x1 and the result should be 1 in modulo 3. And it is the same for this one, 231. I have to multiply by x2 and the result should be 1 in modulo 5. And it is 165 multiplied by x3 and it has to be 1 in modulo 7. And it has 105 multiplied by x4 equals to 1 in modulo 11. So what might be the x1? I'm going to show you here the explanation of this one. I'm going to use here. So 385 multiplied by x1 equals 1 in modulo 3. So if I divide 385 by 3, let me use my calculator, by the way. 85 in modulo 3. The result is 1. x1, 1 multiplied by x1 equals 1 in modulo 3. So it means that what might be the x? It is actually very obvious that x1 should be 1. Why? Because x1 can be any integer between 0 and should be smaller than the 3. So x1 should be 1. So we can say that x1 equals 1. So 231, if I divide by 5, it will be 1. Change the color again. So it is the 1 multiplied by x2 equals 1. It means that x2 equals 1. So if I divide 165 by 7, what is the remainder? 100. And this one is here. 65 multiplied by x3 equals 1 in modulo 7. And what might be the x3? And actually, at first, what is the remainder if I divide 165 divided by 7, which is 4 multiplied by 2 in modulo 7. So here, 165, if I divide by 7, the remainder will be 4. Okay, we are going to use 4. But what might be the x3? It has to be greater or equal to the 0, and it has to be smaller than the 7. So x should be 0, 1, 2, 3, 4, 5, and 6. So one by one, you have to just try and error. For example, if I use 0, as far as I know, the result should be 0. If I use x as a 1, the result will be 4, because 4 still is less than the 7. So if I use 2, for example, 2 multiplied by 4, it is 8. If I divide 8 by the 7, the remainder will be 1, right? So the x3 equals 2. But if you wish, we can just check for the rest of it. For example, if I multiply 3, if x3 is equals or equals 3, just multiply 3 by the 4, the result will be 12. If you divide 12 by the 7, the result will be 5. If the x is 3 equals 5. 5 multiplied by 4, it is 20. If you divide 20 by the 7, the remainder will be 6. If x3 equals 6, 6 multiplied by 4, it is 24. If you divide 24 by the 7, the remainder will be 3. So only one case that x equals to 2. It means that 2 multiplied by 4, or let me write in the same order, 2, 1, which is 8. That's why it is 1. I guess this is clearly understood by yourself. So here we can say that x is x3 equals 2. And now we are going to find the remainder of the 105 in modulo 11, which is 6. Modulo 11. So 105, its image in modulo 11, it is 6. So 6 multiplied by x4 divided by 1 in modulo 11. So modulo 11 is very simple actually. We have 33, 44, 555, 66, 77. So just try to find which 44 or 55 or 66, which are very close to an integer which can be divided by 6. For example, it is 30. Let us start from the beginning. For example, 11, you cannot find any integer that you just multiply by 6 and the remainder should be 1. It means that there has to be something else and one integer. You have to multiply by 6 and plus 1, or you can say that, for example, this one. For this one, you can say that I just find a way. For example, let me do this one as k divided by 11, and this one's I, and the remainder will be 1. So 11i plus 1, it has to be k, and k is 6 multiplied by x4 equals 11i plus 1. For example, if I is, let me say, is 4, for example, is 54 plus is 44 and plus 1 is 45. 45, if I divide by 6, the result will be 3. So if I check if I equals 5, for example, is 55, right? And if I divide this one by 11, the result will be what? This is the 5, 55, 56. If I divide by the 11, the result will be 2. So what is the one of the x4 in this case? And as far as we know, the choice set of 0, 1, 2, 3, and it goes on as 10, 9 and 10. If you wish, you can just check one by one. If I multiply by 0 and 6, the result will be 0. If I multiply by 1, the result will be 1. If I multiply by 3, I'm going to skip this 2. If I multiply by 3, it will be 18. If I divide 18 by the 11, the result will be 7. And it goes on. But if you multiply by 2, it will be 12. And if you divide by 11, the result will be, the remainder will be 1. So x4 equals 2. Is that understood? Is there any question till now? You may raise your hand if you wish, by the way. If you cannot find any time to write, you can just raise your hand and I can give you permission to use your microphones. Is that clear how we find x3, x2, x1, x4? Okay, you have to try. Thank you also. I guess you're the only person in class here for now. So as a result, we are going to use one result column. So what we are going to do? We are going to multiply these two, 385 and 1. Multiply by these 3. 2. It is 2. It is 2 multiply 385 and multiply 1 equals, yes, what is the result? Also, it is 770. Yes, 770. So in this case, now we are going to multiply 2 by 231 and 1, which is 462. Yes. And we are going to multiply by 365 and 2. What is the result? 990. Yes, that's great. So we are going to multiply 105 and 2, which is, yes, 210. Now we are going to take the summation of these 4 results here. What is the summation of the results? Equals 770 plus 462 plus 990 and plus 210. So the summation of the results are 2432. Okay, now we are going to use that result as what is 2432 equals what in our modulo 1155, which comes from here. So the result x equals, let us check, 2432 in modulo 1155. The result is 122. Is that understood? That's great. Now let us do for the second way, the second alternative way. Yes, at first we are going to start with the latest or the last part, which is x equals 1 in modulo 11. So which means that I can rewrite x as 11k plus 1. This is our first step. What is our step 2? In step 2, we are going to start with this one. So x equals, at first, 11k plus 1, which also equals 3 in modulo 7. So in modulo 7, the 11 we can rewrite as 4k and plus 1 equals 3 in modulo 7. So it is, we can say that it is 4k equals 2 in modulo 7. And here the k can be one of the 0, 1, 2, 3, 4, 5, and 6. So you can check what might be the k equals to what. For example, if I multiply by 1, it will be 1. If I multiply by 2, it should be 1 again. If I multiply by 3, it will be 5. If I multiply by 4, it will be 16, and the result will be 2. So we can say that k equals 4 in modulo 7. So we can rewrite k equals as 7i plus 4. How it comes? It comes from as just here, k multiplied by divided by 7. This is I, and this is the result, which is 4. Okay, so now we can say that it was 11k plus 1 at first. Now the k equals 7i plus 4 and plus 1. In the end, it equals 7i plus 44 plus 1 plus 45. Okay, is that clear for now? Now we are going to continue with this step 3, which is this one. This is the step 3, and this is the step 2. And the first one is step 1. Okay, now we are going to continue with the step 3. Step 3, we have x equals to, it says, x at first equals to 7i plus 45. It has to equals to 2 in modulo 5. 7 we can rewrite as 2i. I divide 7 by 5, and the remainder will be 2. That's why I use 2. Plus 45, it will be 0, equals 2 in modulo 5. So in this case, we can say that, this is 0 by the way, we can say that 2i equals 2 in modulo 5. It is very obvious I should be 1, right? So we can say that I equals 5 multiplied by z and plus 1. So I'm going to rewrite as the previous one. This was my x was 7 multiplied by I and plus 45. Now I'm going to rewrite I here as 77, sorry, x equals 77, and I'm going to rewrite one I is here, 5 multiplied by z and plus 1 and plus 45. This is the 45. It's not 9. So here, if I multiply by 77 by 5, what is should be the result? Let me just use my calculator. It is 385 multiplied by z and plus 77 plus 45, 122. Now this is our latest x. And we are going to start with just one step we left. And now we are going to start with the step 4. This is our last step, which is step 4. For step 4, x equals 385 multiplied by z and plus 122 equals 2 in modulo 3. So in modulo 3, if I divide 385, what is the remainder of this one if I divide by 3? Remainder will be 1. Then 1 multiplied by z and plus the remainder of the 122 in modulo 3. Remainder will be 2 equals 2 in modulo 3. And we can say that in this case, if I just send it to the right side, z equals 0 in modulo 3. What it means, z is, if I divide z by 3, the remainder will be 0. So z equals, or let me just show this one as, if I divide z by 3, this is, let's say, m, and the result or the remainder will be 0. So we can rewrite z as 3m plus 0. And now we have to update our x. And now at first x was here, was here 385 multiplied by z and plus 122. And now we are going to rewrite as x equals 385 and multiply by 3m plus 0 and plus 122. We just rewrite the z here. So x equals, it has to be our greatest modulo, which is 1155 m plus 0 and plus 122. So here is our result. The result is, this is our greatest modulo, and this one is the simultaneous x, which is our result. Okay, so it is not very hard actually, but it takes time. That's it. Okay, do not worry about it. You just follow the steps. This is the second alternative, and the other one is the first alternative. In the final exam, for example, if I ask any question about the Chinese remainder theorem, you may use any alternative. I do not force you, or I do not restrict you to use only one alternative. I do not specify the alternatives. you are going to choose one of them. Which one is easier for you? Which one is the most convenient one? You may choose that alternative in exams, okay? So if you think that the second alternative is the easiest one, so you can apply this alternative in the exam. If you think that the first one is the easiest one, you can apply that alternative in the exam, okay? So let's continue. And also we have a theorem too, but this is a very simple theorem. A Fermat, which is a mathematicians too, and also they this scientist also tries to study on the prime numbers too. So in this Fermat's little theorem, he says that if P divides a power of P minus 1 and minus 1, whenever P is prime and A is an integer not divisible by P. So here theorem, what it says, for example, for example here, a power of prime number minus 1 equals to 1 if the mode is prime number. What it says, for example, he says that in Fermat's little theorem, any kind of integer, it doesn't matter, okay? It does not matter. For example, 1987. Power of 10 equals 1 where in modulo 11. It doesn't matter what the integer a is, okay? It has to be integer, of course, but this p or this modulo, it has to be, this one should be the prime number, and this one should be the prime number minus 1. That's it. So in this case, in this Fermat's little theorem, you are trying to find a way to show or to express the integer or the power of numbers, power of the numbers. You are going to just try to find a way to show the modulo, when the modulo should be the prime number, and minus 1. We are going to see our exercises and examples. For example, this one, it is 7 power of the 222. So what can we do in this Fermat's little theorem? So here we are trying to find a way to express that explanation, that expression. It has to be a bit similar to power of 10. How I can rewrite as power of 10 at that part. 7 power of 222 equals what? We are going to say, and it is modulo 11. So as far as I know, if I divide something else, let me say that this is k, and power of 10, it will be 1 in modulo 11. This is what the Fermat's little theorem says. Okay, so what can I rewrite as this one? For example, if I can write as at first 222, can I say that it is 10 multiplied by 22? Yeah, I guess we are going to write the same way, I guess. And plus 2. Can I write at that way? That's great. So whatever it is, 7. So I can use that expression the same as here. So what should I say, or what can I do in that case? Okay, how I can rewrite? Yes, it is the same, not 20. Now we are trying to find just 1 minus, for example, this is 11. 11 minus 1, it is 10. That's why we are trying to find a 10. Here, we are going to find a way to express some part of this explanation. Okay, for example, if I say that it is 7 power of 22, if I rewrite as power of 10, is it correct? No, no. We are trying to find a way to show some integer or any integer, but the power of this integer should be 1 minus the modulo. When our modulo is a prime number, we are trying to find an expression or find a way to show how we can write a way that the power of that number is 1 less than the prime numbers, which is the modulo itself. Yes, Sarah, but the place of the 10 and 22 should be replaced. You have to change the places of these two. So it, yeah. For example, this one is not right. Sorry, let me change the color. 10 power of 22. This is not the case in Fermat's little theorem. You cannot show it as 1 because this one should be less than our prime number. Just 1. 1 minus prime number. So it has to be shown as this one in order to apply the Fermat-Little theorem and multiply by 7 power of 2, which comes from here. Now it is understood. Okay, we are going to see another example too. So it means that if I can write that way, it means that it is still 7 power of 222. So here we know that the result of this part is 1. 1, so 1 multiplied by 49 equals what in modulo 11? So it is 49. So the x should be 5 in modulo 11. It means that 7 power of 222 equals 5 in modulo 11. Okay? We're going to see another example most probably. Yes, for example, this one. It is 8 right here. 8 power of 170. What is the remainder if I divide by 13? So 13 is prime number, and I am going to find a way to express that part as prime number minus 1, which is 13 minus 1 equals 12. So I have to find a way to express 170 as 11. How many times 12 we have in 170? It is 14, I guess. And plus 2. Is it right? So the same procedure we are going to follow. So we can rewrite 170 as 14 multiplied 12 and plus 2, and 8 power of 14 and power of 12 and multiply by 8 square, which is the x in modulo 13. So what we know that this is 1. Why? Because this is prime number minus 1 and this is our prime number. So here continue 1 multiplied by 8 square, which is, let me write it 8 square instead of the square as 64, equals what in modulo 13. Yes, it will always be 1. But there's only one case. That one, that the modulo should be the prime number and the power of any integer should be prime number minus 1. This is the only rules or only criteria we have to follow. Okay, thank you very much. And if I divide 64 by 13, what should be the remainder? Actually, if it would be 65, it would be the 0. So now it has to be as x equals 12. Yes, that's correct. In modulo 13. Okay, that's great. Is there a question? Okay, you can do this one as your, actually, we did this one? No, this one is another example, but I let you to do this one. Let me say this is practice. But if you wish, we can do it. Or let us do just first one, first alternative. I'm going to do the first alternative, but it is better to just for the training, or let me do this one as an exercise. You can do it, but let me do for the first one, the first alternatives, first way, I mean. What we are going to do at first, you can say that let us calculate the greatest modulo, the great modulo, which is 2 multiplied by 3 multiplied by 5 and multiplied by 11, which is, I'm going to use my calculator in this question. Yes, it is 330, which is our great modulo. And now I'm going to construct my table and use the black. So at first I'm going to use modes. It's very straight lines. And the remainders and the specified modulos and inverses, and in the end there will be results. So here the modulo is mod 2. The remainder is 1, which is given in the question, and it is 32 to 330 divided by 2, it will be 115. And what is the 115 multiplied by x1, and the result will be 1 in modulo 2. So in modulo 2, this is very obvious that it is 1. So the result will be 1. In this case, we can say that x1 equals 1. Oof. I construct my table. So here is the modulo 3, and the remainder is 2, which is given in the question. So for the modulo 3, the modulo specified for 3, it will be 110. It will be better to do these questions all together. Okay? So 110 and 110 modulo by x2, and the remainder will be 1 in modulo 3. And it is 2, I guess. If I divide by 2, the remainder will be 2. And this x2 equals 1. And in that case, what should be the x2? It is very obvious that x2 should be 2. Okay, let's continue with the modulo 5. In modulo 5, the remainder is 3. And if I divide by 5, it will be 66, I guess. Let me show it here. By 5, it will be 66. So 66 multiplied by x3 equals 1 in modulo 5. So the 66 will be 1. So x3 should be 1 in modulo 5. So x3 equals 1. So in modulo 11, it will be, the remainder is 4, which is given in the question, and the specified modulo we are going to divide by 11, which is 30. So the 30 multiplied by x4 equals 1 in modulo 11. So if I divide 30 by modulo by 11, the remainder will be 8. Multiplied by, sorry, let me write here 8. This is 8 multiplied by x4 equals 1 in modulo 11. So here I'm trying to find, I use a try and error method. At first, x should be, it might be 0, for example. If I multiply 0, 8, it will be 0. If I take the x1, it will be 8. If I x as 2 multiplied by 8, it will be 16. If I divide 16 by 11, the remainder will be 5. If it would be 3, it will be 24. And if I divide by 24 by the 11, the remainder will be 2. So if you check the results, actually it is very easy to see that it has to be 7. Why? Because if I multiply by 7 by the 8, the result will be 56. And 56 is just above 1, or 1 greater than the 55. So because we have 33, 50, 44, 55, 66. So it means that we are going to try to find just one more of it. For example, 33, it should be 34, but there's nothing, there's no any integer, we can just multiply by 8 to get 45. Okay, if it is 66, for example, if I add one more, which is 67, but there's no any integer, if I just multiply by the 8 and get the result as 67. For example, it's 77, 78, just one more. I cannot find any integer that we can multiply by the 8 and get the 78. Okay, this is the only reason. So x1 should be x4. X4 should be 7. Okay. Is there a question for this one, by the way? So we are going to do the following tables, which is results. So here we are going to take 1 multiply by 115 and multiply by 1, which is 115. Okay, and here is 2 multiply by 110 and multiply by 2, which is 440. Okay, here is 3 multiply by 66 and multiply by 1, which is 178. So 198. Sorry, 198. And here is 4 multiply by 30 and multiply by 7, which is, let me just mark it, which is equals 840. So the total of this one equals, and it is 1,593. Okay, now we are going to use that one. What is the 1,593 equals what it in modulo 330? So what is, let us check. $273. We found it. So let us check our results. For example, it is 330 and we divide it by 2. Here, the remainders I'm going to explain in the detail from the beginning. A quick review, we can say. It is 1, which is given. It is 2, it is 3, and which is 4. This is our remainder column. And now we are going to divide 330 by 2. It will be 115. And this 110 for divided by the 3. And divided by the 5, it will be 66. And if I divide by the 11, it will be 30. So here, what is the inverse of these ones? For example, this one is 115, which is 1. And in modulo, it has to be 1, modulo 2. If it is 110, it equals 2 in modulo 3. And what should be x2 if I just multiply by 2, and the remainder will be 1, which is x2 equals to 2. And it is 66, and it is 1. It means that the x3 should be 1. And now it is 30. The inverse of the 30, it is 8. 22, because if you just do this, the remainder will be 8. So the 8 multiplied by x4 and it equals to 1. So it is obvious, or you can just use the trial and error method and you can get the result as x 4 equals to equals to 7. So here in the end we are going to multiply this all integers, which is 1 multiplied by 115 and 1, which is 115, of course. And for the other one, it is 2 multiplied by 110 and multiplied by 2, it is 440. And for the other one, which is 66 multiplied by 3, which is 198. And the other one is 4 multiplied by 30 and multiplied by 7, it is 840. Now we are going to add this all into together, and in the end we get 1593. And what is the result, or what is the remainder of this one? It has to be 100 in modulo 33 330. The result will be 273. Okay, is there a question? Or you can do this one as for the second alternative if you wish. Yes. Okay. Is there a question? Did you all understand what I mean, or what is the alternative ways for the Chinese remainder theorem? Is there any question? Because next week we are going to start with the cryptography. Okay, then thank you guys for your participation. Oğuz, Sara, and Azam, and also Hadid I saw. Yasin. Okay, I'm going to just close the recording. If you like the video, please press the button for like, and do not forget to subscribe. And if you want to get 5 points from your final exam, please click on this button too. Yeah, just kidding, of course.